for stream. SED stands for stream operator. So if you've worked with a grep command, you can find patterns in the file using grep. But sometimes you might want to actually change what you find in the file. So maybe you want to change a FASTA heading, maybe you want to get rid of a special character. Some of the phylogenetic software people use tend to need properly formatted headers. You need to remove special characters from there. So grep will allow you to pick up those characters, but not to modify them. But if you want to modify them, then you use something called the stream editor or SED. And I'll show you why you do that. Also, if you want to print only certain lines in a file to use for another program or to check, SED is quite useful for that. And I usually use SED. I find it really useful for finding, substituting, and formatting text as well, especially in files and in your FASTA headers as well. Because some software also want it to be like 10 characters or something very specific. So the basic SED syntax is just SED, which is the command for stream editor. You open your quotes. These are your tick marks. Then you have your S, which is your substitute. You have a slash. And then your first pattern is in the first slash. Then you have your second slash, and then that's the pattern to replace it. And then your input file. You need to give it an input file for it to actually work on that. So the S after the SED in the command is for substitution. You can have other flags over here, but I tend to use the substitution one quite a lot. So that's the one I'll stick with. And for example, if I was to run this command SED substitute CHR, which is my first pattern with chromosome, and then I give it the path to where I want the file is, which is called genes GFF. SED will read the file and look for matches to the pattern line by line. So that's one thing you have to remember by SED. When it reads in a file, it's reading it to the stream editor. And your stream editor in this case is your standard output, which is your screen. And SED also works by reading each file line by line. And then it's sent out to the screen. So this command over here with the substitute has changed this from CHR to chromosome. So that's how I've formatted this file using just the substitute command. But if you do have a stream of characters on my screen, it doesn't really help me as I need to use the actual file that I modified for use in another program. So I think in the last part of the practical, you'd have probably seen something about file redirection, where you send your standard output, what comes on your screen, into a different file. So one generally redirects output from the screen to a new file. So usually when I run my SED command, first I pipe it into less to make sure it's doing what I want it to do. And then when I'm happy with it, then I send the output into an output file. That just helps me debug and make sure that when I do have a file, it doesn't have the errors in there. So the redirection is just your input file, and then you use the greater than sign, and you give it the output file name, and it will create the output file if it doesn't exist. If it exists, it will overwrite the file, similar to the CP and other commands. So for example, if I do SED substitute CHR for chromosome, and then I go to the genes file, and I send the output to the SED output genes GFF file. So the previous example I gave before, there was a bit misleading for a reason. So let's say if I need to format the file from its current tab limited format to a CSV one for another program, I type SED, and then I look for the tab, and I substitute the tab with the comma in the file. So what it's done here is it's substituted the tab CHR, the first tab, with a
Okay, use the arrow, the left arrow.
File line by line, and it matches to the first pattern it finds in the line. So for example, when I did the CHR to chromosome example, CHR only appears once on each line. And once SED finds that first match, it then changes it. If I wanted to substitute the tabs, the multiple tabs on the line, on each new line, but SED will only match to the first instance of it and only replace the first one. And that's the way SED's default behavior is to substitute the first match on each new line, but you can actually change this behavior. So you can change this behavior by using what's known as a global flag. So that's just adding a G at the end of it. So if I rerun my command, sed substitute my /t, which is my tab character, for a comma to get a CSV file, and then I use the -g flag, which is the global flag at the end. It will substitute every single tab in the file, regardless of how many times it matches it. So that's how you'd force sed to work on more than one match per line. So one can also use sed to print out specific file lines in a file, for example, a row. So if I wanted to extract lines 1, 2, and 3 from the genes GFF file, I'd say sed 13p, and then to give it the file name. So 13 means this is a range of lines to print out, and the p means print out to the screen. And as you notice, there's no slashes, no s, no g, and that's because we're just extracting lines. We're not matching or modifying any characters. So we're just asking sed to print out specific lines in a file. So for example, if I do this with the genes GFF file, I say sed 13p, it will print out everything though, not just the lines I wanted to print out. And there's a reason for this. And then so it will print out the whole file, and it add lines 1 and 3 within the file, which is here. So it's added it there, oops, and then it's added it there in red. And there's a reason for this. So recall sed's default behavior is to print everything out to the screen. So what you want to do is you want to use the -n option to prevent sed's default behavior of printing everything out to the screen. So for example, if I just wanted to print out lines 1 and 3, I'd say sed -n, and I give it the -n switch. And that's to suppress its default behavior and only print out what I've asked it to print out, which is lines 1 and 3. So if I want to print out specific lines, e.g. in a file, for example, 1, 2, 3, then 5 and 7, I'd use this kind of construct, sed. I'd open my tick marks, 1, 3p. That's my first range. Then I close it to a semicolon. Then I give it my my second last line, which is 5. And I have to put the p there because I want it to print out. And then also do another semicolon here. And then I give it the last line, which is 7. And I can do this multiple times. I can put another semicolon and do like 10p and stuff like that. So that's just one way of getting your files, lines of your files printed out. And if you run this command, it should give you this kind of output over here. So sed has a lot of what we call wildcards, and they're really useful characters because they really help in terms of pattern matching and give you a lot more finesse when you need to make a pattern or substitution. And because I usually use it for sed for matching and formatting files, so I do need to have a really good grasp on how to match my patterns and where I want them to be, else I might make some errors in the file itself. So you have what you call the caret, which is this character here. And that is means to match the start of a line. Then you have the dollar character in sed, which means to match the end of a line. You can have A to Z characters of the alphabet. This is used to change cases, and the UN and ampersand for uppercase, and L, capital L, ampersand for lowercase. But I'd suggest if you're going to change just cases, then maybe look at the Unix command tr for changing cases, because that's a lot more efficient than doing it in sed. And if you want to print out odd number lines in your file, you'd use sed -n, p, and then n. Or if you want to print out even numbers, then you flip the n and the p in the construct itself. So here's just an example of using sed to substitute, to add organism at the beginning of the file. So I'd say sed substitute and then match the first thing at the beginning of the file, which is the chr, and then add organism underscore to it. So it adds this construct here to my chromosome. If I want to add organism to the end of the line, I'd say sed substitute, and then I put the $sign, and then my underscore organism, and then genes GFF, and it will add organism at the end of the line itself. So that's one way of getting to the beginning or the end of the line with a lot of specificity. And then here's just an example of substituting cases from lowercase to uppercase in the genes GFF file. And as you can see, I've used the S, which is for the substitute, and I've used the -G flag, which is for globally. So this will do it for every single line then. If I do it only without the globally, the global flag, it would still work because it's still looking at the end of every line because SED reads a file line by line. But if I have multiple instances where I want to add this, which this case I don't, because I only want to add it either to the end or the beginning, I don't really need the global construct, but I like using it just for completeness. For more specific control, you can use the pattern to be matched. For example, I can use start of the line or the caret and then CHR and then a star just to as a wildcard to match everything. And then I'd use the organism underscore over there. So it more or less does the same thing. As well as even at the end of the genes. So for more examples on using SED and syntaxes, I've just put some URLs over here. And these will be really good to look at. I suggest maybe you should use SED. There's a practical that I've created, which we can work through, and maybe spend an hour working through that practical, and I'll be online to help people with that. Are there any questions? Okay, if there are no questions, then maybe we can download the practical on the canvas for the SED practical. This would be on the in your canvas in the modules on the advanced Linux. It's the SED practical for the bioinformatics workshop. So you can go through some of these exercises. What you might need to do is you might actually need to change to my home directory to actually run some of these things. But I'm hoping when Michael comes back from the breakout room, he can help put those files somewhere where everyone can access them other than my home directory. A lot of these commands, you can copy and paste them, but you're going to have formatting issues because they're done in MS Word, so it doesn't contain the correct tick marks. So maybe I suggest just trying typing it. And also when you type it, you will get errors, and those errors are useful because they'll let you know, give you an idea of what you're doing wrong. So I think this practical should take roughly an hour. So it's 10 o'clock South African time, so that should be 11 o'clock Kenyan time. I think we're running till 12 Kenyan time, if I'm not mistaken, or 1, if I'm not mistaken.
Yeah, that would be 12:30, but yeah, I think we could go up to 1 because the break could be up to 2.
Okay, yeah, because I think what we'll try and do is we'll try and cover a lot of this today. I think the SED and the AWK are more important. The Bash, I think if you're first-time users, I think Bash might be a bit too much, but I'll show you some nice examples with Bash and where I use them. But yeah.
Okay.
And then from there, I'll go on to the bash one. So the bash one, I don't think you'll get to do the bash today, but if you do, it's great. There's some scripts there which you can have a look at and see. Let me just quickly share my screen. Okay, so these course materials are created by Dr. Almagulia and myself, and they're based on some of the course materials in Wellcome Trust, NGS, and H.E. Barnett, NGS Bioinformatics course 2021. So what is AWK? So AWK is a scripting language which has a lot more text processing capabilities for data extraction, comparison, and transformation. Similar to SED, it's available on most Unix operating systems and Linux operating systems. So it's one of the core utilities that you find installed there. And this is why we like working with Linux commands and SED and stuff like AWK, because you do find them in a lot of Linux distributions as well. And they tend to be more or less similar. You do have variants, like, the Mac OS has different ways of working with SED than the ones we're used to on an Ubuntu machine. And that's because it's not the GNU tools or utilities. So AWK is named after its inventors, Aho, Weinberger, and Kernighan. And it's used when one wants to extract fields or makes comparisons or filter data and just general data wrangling. It's a really useful tool as well, especially when you work with data that's in tabular format. And that's because AWK allows one to work with data that's delimited as well. So a delimiter would be like your comma, your CSV separated file, your tab, or a space. Similar to SED, it reads in a file line by line. So although it's very useful, sometimes if you're working with massive files that are like, 3 million lines long, it can be a bit cumbersome. So do be a bit careful about that. Where it's different to SED is that when it reads in a line, it splits the line into fields. And when I say fields, think of those fields as columns. So you have a lot of data formats in bioinformatics which have delimiters, such as your tab or being a comma separated value. And because of AWK's text processing capabilities, it has lots of inbuilt functions that allow one to manipulate these files. And unlike SED, SED allows you just to manipulate text and it works on strings, whereas AWK can actually work on columns within a data set because it splits it. So the basic AWK syntax is your AWK, and then your minus switch, and then your options, similar to your Unix command or your SED command. And then you have your optional selection criteria, and then you have your curly braces where you have your action, and then you have your input file. So this is where the syntax is a bit different because you've got your selection criteria, and then you have the action you want it to do. So for example, in this construct, I've asked AWK to print out the first column of the genes. So when I say AWK minus F, so I'm setting my field delimiter to be a tab. So the /t indicates the tab character. And then I'm asking AWK to print out $1 genes GFF. So $1 would be the actual first column of the file. Similar to SED, AWK will print out the output of the standard out, which is a screen. If you want to save the output, you need to redirect it to a file. And where it's different from SED is AWK has inbuilt variables called $1, $2, $3, and these variables map to fields separated by whichever delimiter you choose when specified. Such in this case, I chose the -t. And what those $1, $2, $3 indicates are just the names of the columns that you have your fields, your data has been separated into when you split it with AWK. So it's usually useful to determine the number of fields a file has in the start. So in order to do that, you do AWK and then your ticks and your curly braces, and then print NF. So NF stands for number of fields. And it's an inbuilt AWK variable that's defined each time AWK reads in a line. So if I do that for the genes GFF file, print number of fields, I get 9, 10, 9, 8. And this time it's splitting the number of fields for each line it's reading in. So there are two records in line 2 and line 5 that seem to have 10 fields, and one in line 4 that has 8 fields. The rest have have 9. So any reasons why that would be in the genes GFF file? You can do it less and look at the file right now if you like. So what we'll do is let's just print out those lines to see what's going on there. And what you can see is it looks like there's a space over here and a protein. So an annotation column for column 4 seems to be empty as well. For record 4 seems to be empty, which is here. So when because the file is tab separated in the previous construct, we do not tell awk to split the file according to a delimiter. So all we asked it to do was just print the number of fields, and by default it splits on space. So if I ask awk to actually set my field delimiter using the -f flag to a T and then print out the number of fields, you'll see I get 9999, which is the correct way of doing it. So I'm just going to go through some examples of awk usage. This is just more to give you a bit of a background and introduce you to awk. And I think in the practical, you will get to mess around with some of these commands. So it just gives you a bit of a background on there. So as I said, the basic syntax is awk, your option minus your options, such as your field delimiter, your optional selection criteria, and then the action you want, and then the input file. So you can use the optional selection criteria to do some filtering on the files. For example, the genes GFF file. So over here, I'm going to say awk -f, which is my field separator, is a tab. And then if $1, which is my first column, is greater than chromosome 1, then print 0. And I'll show you what the print 0 means. And so what I'm asking you to do is to look for anything that's greater than chromosome 1 in the first field it finds, in the first column, which is $1. So that will print all genes that are greater than that. And the print 0 means print the current line it's reading in. And awk, where awk is great is it recognizes mathematical operators such as a greater than sign, which is very useful when you're doing some kind of data processing. And the construct above will do 2 things. The optional selection criteria is to use field 1 of the line being read in and check if it's greater than chromosome 1, which is this part here. And as it reads the file line by line, it will print the line $0 only when the condition is met, which then gives you all of these over here. It's useful for extracting lines based on a field from a file. For example, all entries for chromosome 2 only. I mean, you can grep it as well, but it's also, if you want to filter it as well, you can also do it this way. So the awk, my field separator is my tab. And then my first column should equal to. So use a double equals to sign and not a single equals to, because a single equals to in computer language means you're assigning something to a variable. So here we're saying if it actually is equal to or it matches this, then print out the line 0, which is what it's reading in. So that way I can extract everything that's got a chromosome 2 annotation. And you can also track fields from a file and put them into new ones. So like, let's say if you've got columns from like one file and you want to merge them with columns from another file, you can also just tell awk to print those columns. So I can print 1, 2, and 1, 3, and 7 from the file in genes GFF, and then I can send that output to another file as well. So that way you can also take subsets of your data that you need. But the problem I get here is the output doesn't seem to be tab delimited as it originally is in the original file, and some programs do need a delimiter as well, rather than space. So if I want to get the output in a tab format, then I need to change awk's default behavior. And you can do that by using what's called the OFS, or output field separator. So for example, in this construct, I'd say awk, my field separator, which is my tab, then begin, because you need to tell it to start what you want it to do. Then my output field separator is a T. And then I can print out the lines and it'll print it out for me in a tab format. So these kind of constructs are quite useful. And I mean, you use the slides and stuff to build up your own constructs, and you should find them quite useful when you're working with data. So begin is an awk variable that tells awk to execute the action in the first set of braces once the first line is read in. So that's what I'm saying here with the begin statement, is to execute this. So as soon as you read it in, execute this. And what I'm asking to execute is my outfield separator should be a tab. And I set that variable to a /t, which is a tab. You can also use awk to replace every value in a specified field. For example, awk minus ft begin, then here's my outfield separator, and then $2 equals to Homo sapiens, and then print 0. So I've changed that into Homo sapiens as well. And this is sometimes a bit better than doing it this way than doing it with SED, because sometimes with SED you have unexpected consequences where it might match something else in your file which you're not sure about. Whereas here you're actually specifying which column you want exactly to be changed. So it does give you a bit more specificity than SED. So you can also combine multiple patterns in awk. So you use the double ampersand. And to mean if it meets criteria 1 and criteria 2. So for example, if I want chromosome is equal to 1 and chromosome and my column 3 equals to genes, print it out, and then that will print it out for me and just extract what I want. You can also meet criteria 1 and criteria 2 and criteria 3. So this is similar to like how you change your kind of like piping stuff from one Unix command to another. Here you're kind of joining them to get like an optional selection criteria, and you can combine multiple ones at the same time. I suggest instead of trying to create one long line of filtering criteria, try and do it in bits and pieces, because in that way you can also look at your data and make sure that it's doing what you want it to do. And then you can always go back and then create one long command. I can also use the double pipe as an OR condition to mean do it if it meets a condition or criteria 1 or criteria 2. So if my column 1 equals to chromosome 1 and my column 3 equals to genes and or print it out. So it will print out genes, repeat, gene, and repeat. So the double pipes in OR does mean an OR condition. You can do multiple conditions and filter based on numerical values instead of just on strings as we've done. So for example, if I want to get like the expression or coordinates, I can say column 4, which is $4 should be less than 1,100. Or I can even set it as value greater than that. And that's because awk recognizes mathematical operators, and that's what makes it so useful. You can use it to perform basic calculations based on some criteria. For example, I'm asking it print, take column 5, the value of column 5, and minus it from the value of column 4, and add 1 in the genes GFF file. Reason I'm doing that is due to the general feature format where the sequencing numbering starts at 1, and it's different to the bed file format where the sequencing numbering starts at 0. So that's why I'm adding the +1 there. I think you probably covered that a lot more in the file formats though. So you can also use awk to do basic arithmetic. I mean, it's easy to do it on the command line and you can write functions for this, but if you're going to do something a bit more complicated, I suggest use something like R that's more suitable to that, or Python. But I mean, you can do some simple mathematics and stats with it. So for example, you can add up the total length of repeats using a variable. And here I'd set my variable sum equals to sum plus 5 minus 1, and then print sum, and then it should give me this number there. So the variable sum is being set to 0 over here. So when I start reading the file, set my count sum to 0. And then I'm assigning sum here, which is what is the total of this equation. And each time the line repeat is found, then the calculated length of the repeat is added to the variable sum. And then you need to have an end statement, which tells awk what to do once all the lines of the files have been read and it comes to the end of the file. And in this instance, I'm asking awk to tell me, okay, give me the total value of what's contained in the variable called sum. You can also use it as a counter, such as in this case over here, at the bottom construct, where you ask awk and then you separate by fields. You begin reading the file from the beginning, and then you set your sum value or variable to 0. And then you do sum equals to plus as well. which should be 5 minus 4 plus 1. And that should give you something similar as well. I think the construct on top here is actually not correct. I think that should be a double equals, if I'm not mistaken. You can use awk to calculate mean scores in the column of 6 for the file. For example, you could give it this equation. We use the second variable count is set to 0 and adds 1 each time the gene is matched. So this keeps the track of the number of matches to a gene. And that's my variable over here. And count, I've kept it to 0. And so the reason I do that is because then I get the total value of the gene expression here, and I'll divide it by the total count of number of genes that it's found in the file. And that's what my end statement is basically telling awk to do. So there's more information and usage on awk and examples over here in this. I just like to say thank you to Amal and Aishibadet for this. Okay. Do we have any questions at this stage on the awk stuff?
Okay, I have a question here.
Yes.
Okay, thank you, Samir. So this awk, the awk syntax is how are we going to use? Is it purposely for creating tables, or after you have generating the data, so you want maybe to create tables and presentation of data, maybe in table presentation. So is it the one which is we are going to use it in Linux? Or
Look, I think awk is useful if you're going to subset your data. So what you do is so if you want to draw nice tables or if you want to draw graphs, I think use something like R or Python for that. Okay. But I would suggest if awk is useful if you're going to pre-process your data to use for another application like Bioinformatics Software. So for example, you've got like 10 columns of your data, but your input software only needs 2 columns. So then you can use awk to do that. So I think see awk more as a data processing tool rather than a tool for actually finishing your analysis, because I think you'll have specialized programs that do that. Okay. It's a really good way of filtering sequences and looking at stuff really quickly as well.
Okay, so in short, you may say that you in sequence maybe you can generate a lot of information, but there are some information which you need. I think is it that what you mean, or?
Yes. So maybe if you want to take out some information about your sequences, or because sometimes when you get data, you don't want to use all the data columns. You might just want to use some of it.
Okay.
Or if you've got a file of like, let's say 10,000 genes, but you're only interested in extracting 5 genes that you want. And this is useful because, usually when you go to databases and you download data tables, it really has more data than you need. So if you want to extract your data from those data tables, then, something like awk and SED would be quite useful for that.
Okay, thank you so much.
But yeah, its main utility is text processing and filtering. So I think that's where you tend to use it in pre-processing of data. Okay, are there any other questions around?
You got muted.
Okay, if there are no questions around awk, then what I'll do is let me go to the Bash presentation quickly, and then we can break for lunch in the next 9 minutes. So I'm just going to cover the Bash stuff really quickly because I don't think you're going to get a chance with today's practical, and I think it's better you spend time learning Linux, SED, and awk rather well than trying to learn everything and rather not so well. But these materials will be there for you to reference, and the scripts are there as well for you to reference. So do spend some time going through them, even if you're just doing a lesson, looking at what they look like. So yes?
You're not seeing the whole screen.
Oh, okay. Let's do that. Let me stop sharing. Sorry, my computer seems to be hanging. There we go. Okay, let's go to this. Share screen. Okay, is that better?
Yep.
Okay.
Maybe present a view and then you're good.
Just want to put in presenter view. It takes like a couple of seconds before. Okay, is that better?
So again, I guess maybe you can just go on, because when you put presenter view, it also shows the next slide and also the other slides.
Oh, okay. I need to switch the view. Okay. I see what you mean. I need to switch the view. Okay, I'm just going to keep it like this then. Is that fine?
Yeah, sure.
Okay, so currently what we've been doing, if you notice with the AWK and the SED and the Linux, is we're using single commands to do various operations on input files. But where you find Bash useful is if you want to do the same operation on 1,000 files. So what you're going to do is you're going to loop over each file, open it, do your FASTA QC, close it, stuff like that. And it'd be nice to organize these different commands and run it once as a script rather than run each command individually. And if you're going to do the same things over and over again, then it's better to put in a script similar to what you guys have been doing with HPC when you create your QSub or your whatever scheduler you're using. That's what you put in your script, kind of. Bash is very useful, but I think there are more modern programming and scripting languages such as Python and R that are more reused and more complicated tasks as well. And they have really good numerous inbuilt functions and libraries. And I think if you're going to invest time in learning to script, then I'd suggest that maybe look at stuff like Python and R. Bash is there, it's useful to know if you know it, but if you're going to invest a lot of time in learning to program, then maybe Python and R is more suitable for you. So some Bash basics. One creates a Bash script using a text editor such as Nano. A Bash script will be saved with a .sh extension, and it would have a header line that provides the path to the interpreter to execute the sys, to execute the script, and let Unix know that's a Bash script, and that's this bit over here. You should also change a .sh bash script file permissions to be executable. So for example, chmod +x or chmod 755. So then it can run as an executable script, and I'll show you why. So if you go to my directory, I think bash scripts, you'll see there's something here called hello sh, which looks like this. It's got the thing on top to tell Linux that it's a bash script. And echo means just print. So if I run the script as bash hello.sh, it will print hello world. If I do it like / and then the script name, it will tell me permission denied because it's not allowing me to execute it. So I need to change the permissions to become an executable shell. So that's one way of running a bash script, is by saying bash and then the name of the script. Or this is another way of running a script if it's an executable. So you can also just type in the script name .sh if it's also executable. So you use the first option of bash when the script does not have the executable permissions. So that's why we try to make it make them executable. Second option is when the file has executable permissions. And the third one is when you also have executable permissions as well. And the first two ways of running the bash script assume you're in the same directory as the script. The third one actually is not assuming in the same directory as the script. And I'll show you why, because that's how you add it to your path. So you can add the location of the script to your path variable, which would be globally accessible when you're logged into your terminal for your session. You just type in the script name. So if I do pwd, you get home, user account, and then where you are. Then if I cd and I go up one directory, so when I try and run this, it's going to tell me it cannot file the file. But if I do export path and I give it all the way to the bash scripts folder, and I run it wherever I run it, it will run then. So that's why it's also important to know about your paths and your navigation and where your data sits and where some of your files sit on the Unix Linux system, and especially because your files will be your input to your program. So a general format of running a bash script would be your script name and then your input file, similar to, I guess, what you'll be doing with the HPC. So there's a test file, a file called test file, which you could use as input. And what I'm doing over here is I'm asking it to echo the file name is $1, and then just print the first 2 lines of the file itself. And this is the output it will give me. The first 3 lines of the file are test file line 1, test file line 2, and another line. So it's actually going in there and printing the first 3 lines. And here, this is a Unix command. So you can also use Unix commands in a bash script as well. So basically what I'm doing is I'm storing the file name in a variable called $1, and I'm printing out the file name over here. Print out a space for formatting, and then store the number of lines provided by the user in a variable called $2. And the first 3 lines of the file are, and then I'm asking it to head -2 and $1. And then use the values in variables $2 and $1 for obtaining number of lines entered, values, and print them out. So I know it sounds a bit complicated and stuff, but I mean, when you start working with this, it becomes a bit more straightforward. And just something to remember is that the variables $1 and $2 are user defined and they're not specific to bash, similar as they are to awk, where they stand for each column. You can actually change them and make them more user-friendly and easier to read by using good variables names, which is good programming practice. So for here, instead of using $1, $2, I'd say first $number of lines in the file name in my $file name are, and then I use another variable called your number of lines. So that's what's meant by using good variable names. It's just some general good practice, and this applies to whether you're using Python or R or Perl. You should use the inbuilt error flags within the programs that it provides, because this helps you output and debug stuff a lot better. And this is also the thing with bash is you got to be careful is if you don't set the -EU, what happens is bash will run through the whole script and the whole file, and even if there's an error, it will still continue and will only terminate at the end of it. So what you're trying to do over here is asking bash to, if you, as soon as you encounter an error, please exit, and that then helps you debug and then fix your program or your commands. Other things, you should provide good help error messages. I mean, you should see this bioinformatic tools. You should have comments, lines of the script that begin with a hash or ignored by interpreter and then used for commenting about code. And also use good informative variable names. So here's an example of a bash script. You've got the start telling Unix it's a bash. We've set the flags to exit. This is then the parts in a hash which are commented out and let the user know what the script is doing. Usage to be named variables. Then here you're doing a check if the input file exists. Then you're giving an error message, cannot find the file name, cannot continue, and exit. And if we're here, then the input file was fine, then continue doing what you asked it to do. So this is a lot more human friendly and easier to read. And I think somebody coming in can understand what the script does then. An inbuilt variable, which is your $hash, which should be equal to 2 options provided to script. If not equal to 2, then execute this block of code that starts from the beginning and then terminates at 5. So if I'm putting in, type in the script name and I don't give it 2 options, it's going to exit and tell me it can't find the file, the second file. And you're also doing a check here to see the file name exists and is provided correctly. If not, then exit the program. Otherwise, bash will continue running through the program itself. So these are some of the examples of the scripts in my directory, which you can try. Hopefully they'll be able to commit them to GitHub later today, and then you can download them and run them on your own time. One of the most useful things I find about Bash is the for loop. So usually working multiple files, you like to run the same operations as file of one go rather than individually. And during the break, I'll post in a command that I'll help a friend work on to actually iteratively download files using a list of accession numbers using a Bash for loop. So you can have a look at that. But I find the for command, especially because with NGS files, you're working like with hundreds and thousands of files. So you want to execute the same thing on all those files. So your basic usage is for your files in your directory, and then you pattern match them, you do your operation, and you dollar files and done. So an example I've given here, which you can try out in the practical, is for file name in loop files, there's a directory called loop files, match all the files, and then do a WC count, word count on the file name. And then I'm asking it, then you say done to tell it to terminate. I'm just going to quickly go through this because I think you might encounter this. So it's just basically some basic information on running bioinformatics programs. So a lot of the bioinformatics software programs are run via the command line, which is why you're doing a Unix Linux session and working on the server. They do require input files to do the computations and then write these results out to your output files, which is then what you work on for your analysis. So a good bioinformatics program software package usually has a version number and a software license, options and parameters to choose from, provides the information, the options and usage of the program, documentation on how to use the software in various options, and usually use a good user base and support. And hopefully there should also be publications that you can also refer to and cite the software. So usually your bioinformatics programs are installed on a Unix system and available system-wide. You might have to set the $path variable to access the program outside of the program directory, similar to what we did with the Bash script. And you can also access the tool's name by just typing in the name of the tool. So for example, if it's SAMP tools, you just type SAMP tools. If it's BCF tools, just type BCF tools. I'm not sure what's exactly loaded on the server you're working on, but I think when you're working with other software, you'll be using those tools. The usual syntax for running a tool is similar to the command line structure that you've been working on with Unix Linux. You have your tool name, your command from the tool, the optional parameters for that specific command. Then you need your input file or your output file or print to screen if no file is specified. The optional parameters for specific command are usually provided in the format of a Unix style flag with your switch, your minus switch. And I think if you're going to use the software because you want to understand it and use it for data analysis, do spend some time going through the documentation and tutorials and examples of how people use it, because that'll get you off the ground a lot faster than trying to just hack at it without getting a good overview on what you're trying to do. And I mean, tools do differ in terms of the user syntax as well. So do be a bit careful about that. So some of the common errors you're going to get when you're running bioinformatics tools is the most common one I come across is not providing the correct path to the input file or specifying a wrong path for an output file. So what you can do to do that is try and running the program in the directory which has the input files or provide the complete path to the files, which is what I usually do. And I guess if you're creating your bash scripts for your HPC work, you probably see that some of the paths you have to provide in there. Another common error is not providing an output directory or an output file. Sometimes the input file might not have contact or be correctly formatted for the tool to use, which is then why you go back to using stuff like SED and AWK to help you quickly process that data to get into the format you need. Most bioinformatics tools do provide some error messages. Some of them can be quite cryptic, but I think spend some time going through them because they do make sense. For example, if I just run this command on this file, I get an error message saying to run without a reference requires a faster reference option by default. So I need to use this switch if I want to run this tool without a faster reference. And do have a look at them. So like if I run it here, again, with no reference, my file failed to open my file because my file doesn't exist. So I'm giving it a file that really doesn't exist, and that's why the program can't open it. So it says it failed to open my file. And these are just some useful links. I think if you're going to do Bash, have a look at this because this should help you a lot more on that. And with that, I'd just like to conclude. Thank you. Are there any questions? Okay, I guess if there are no questions at this point, I guess we can break for lunch. As I think we're 6 minutes over. And then we can continue the practical in the afternoon, the SED and the AWK practical.
Okay, thanks. Thanks, Sumir. So we can all go for lunch and then come back at 2 p.m. So that you can continue with the practical. If I'm going to stay on, if you have any problem logging in, just put up your name in the chat again, and then we can see how to sort you out so that at 2 p.m. everyone is doing the practical session.